On most clear nights, somewhere above the Earth, the moon is visible. Sometimes it rises slowly over distant buildings. Sometimes it hangs pale and faint in a bright blue afternoon sky. And sometimes it glows quietly in the darkness, illuminating clouds and rooftops and empty roads. For thousands of years, people across the world have looked up at it. The moon has been a clock, a calendar, a companion in the sky. But it has also been something else, a familiar face. Because no matter when you look at the moon, no matter where you stand on Earth, you are almost always seeing the same side, the same shapes, the same patterns of dark plains and bright highlands, the same arrangement of ancient impact basins that formed billions of years ago. To the casual observer, this might not seem unusual. After all, the moon simply appears to hang in the sky, slowly changing its phase from crescent to full and back again. But if you stop and think about it for a moment, something strange begins to emerge. The moon is orbiting Earth. It is moving through space at nearly 1 kilometer per second. It completes a full orbit roughly every 27 days. And yet, despite this constant motion, despite traveling more than 2 million kilometers during each orbit, the moon keeps the same face pointed toward us. It does not slowly reveal new continents the way Earth rotates beneath its clouds. It does not spin freely like a tumbling rock. Instead, it seems almost locked in place. The same craters, the same maria, the same silent landscape that astronauts visited half a century ago. At first glance, this might give the impression that the moon does not rotate at all, that it simply circles Earth like a perfectly balanced coin. But that interpretation would be misleading. In reality, the moon is rotating. It turns slowly on its axis, very slowly, exactly once during every orbit around Earth. One full rotation, one full orbit, both taking the same amount of time, about 27 days. This synchronization creates a remarkable alignment. As the moon travels around Earth, it turns just enough to keep one hemisphere always facing our planet. From Earth's perspective, it appears motionless, but in space, a delicate dance is unfolding. Orbit and rotation moving together in perfect step. Astronomers call this phenomenon tidal locking. It is a special kind of gravitational relationship between two celestial bodies. Over immense spans of time, gravity can reshape motion itself. It can slow rotation, it can stretch and distort worlds. And eventually, it can guide an orbiting moon into a state where one side always faces the planet it circles. This is what happened to Earth's moon. Long ago, shortly after its formation, the moon likely rotated much faster. Its young surface spun freely beneath the sunlight. Days and nights passed quickly across its rocky terrain. But Earth's gravity was constantly pulling on the moon. Not evenly, not gently. The gravitational pull was slightly stronger on the side facing Earth, and slightly weaker on the far side. That difference created a subtle stretching force, a tiny distortion in the moon's shape. Over millions of years, that distortion produced friction inside the moon's interior. Friction that slowly drained rotational energy. Little by little, the moon's spin began to slow. Not abruptly, not dramatically, but gradually. Over tens of millions of years, then hundreds of millions, then billions. Eventually, the moon reached a quiet equilibrium. Its rotation slowed until it matched the time required to orbit Earth. And when that happened, something remarkable occurred. The same hemisphere remained facing Earth forever. The Moon had become tidally locked. To us, it feels natural, normal, almost expected. After all, every photograph of the Moon we see from Earth shows those same familiar features. The vast dark plain of Mare Imbrium, the bright rays of Tycho crater spreading outward like frozen light, the smooth basalt seas that ancient volcanic eruptions once filled with molten rock. These landmarks form a face we know well. In fact, it has become so familiar that we often forget an important detail. There is another side of the Moon, a far side, a hemisphere that remained completely hidden from human eyes until the year 1959, when the Soviet spacecraft Luna 3 captured the first photographs of it. The images revealed a landscape that looked very different. Far fewer dark maria, more craters, more rugged terrain. For centuries, that half of the Moon had remained unseen, simply because the Moon never turned it toward us. Tidal locking had quietly concealed it. But here is where the story begins to grow more interesting. Because for a long time, people assumed that this arrangement was unusual, perhaps even unique. Earth and its Moon might have formed a rare gravitational partnership, a special case among the many worlds of the solar system. But as telescopes improved and spacecraft began exploring other planets, astronomers started noticing something surprising. The same pattern was appearing elsewhere, far beyond Earth, far beyond the familiar orbit of our Moon. Around the giant planet Jupiter, several large moons circle endlessly through space. One of them is Io, a volcanic world constantly reshaped by erupting lava and towering plumes. Io races around Jupiter once every 42 hours, and yet, just like Earth's Moon, Io also keeps the same face turned toward its planet. As it travels around Jupiter, it rotates once per orbit, perfectly synchronized, always presenting the same hemisphere to the massive gas giant below. Then there is Europa, another of Jupiter's moons, a world of ice, smooth and pale, crisscrossed by dark fractures that may conceal a vast ocean beneath its frozen shell. Europa behaves the same way. One rotation, one orbit, one face, always looking toward Jupiter. Further outwards still, beyond Jupiter's vast gravitational reach, another giant planet waits in the darkness. Saturn. Encircled by its luminous rings, accompanied by dozens of moons. Among them is Titan, a world larger than the planet Mercury, wrapped in a dense orange atmosphere filled with nitrogen and organic haze. On Titan, rivers and lakes are not made of water, but of liquid methane and ethane. Rain falls, clouds drift. And yet, despite its alien weather and distant orbit, Titan shares something in common with Earth's Moon. It too is tidally locked. As Titan circles Saturn once every 16 days, it rotates once on its axis. Again, the same pattern. The same strange alignment, the same quiet gravitational arrangement, one face toward the planet, forever. And Titan is not alone. Many moons throughout the solar system behave this way. Small moons, large moons, icy moons, rocky moons. Again and again, astronomers observe the same phenomenon. A moon orbiting its planet while turning just enough to keep one side always facing inward. At first, this repetition might seem like coincidence, but the more examples scientists discovered, the harder it became to dismiss the pattern, because the moons involved were very different from one another. Some orbited gas giants, some orbited rocky planets, some were covered in ice. others were volcanically active. Yet, despite these differences, their rotations followed the same rule. One rotation per orbit, a synchronized rhythm written into the architecture of planetary systems. The realization slowly began to emerge. Earth's moon was not a rare exception. It was simply one member of a much larger family, a family of worlds shaped by the same gravitational process, a process powerful enough to slow the spin of moons over billions of years and guide them toward a shared state of balance. But this raises a deeper question. Why should this happen so often? Why would gravity repeatedly guide moons into the same rotational pattern? What is it about orbiting a planet that causes a moon's spin to gradually slow until it perfectly matches its orbital motion? The answer lies in a quiet but persistent force that operates throughout the universe. A force that stretches worlds, generates heat deep within their interiors, and slowly reshapes the motion of celestial bodies over unimaginable spans of time. A force known as tidal interaction. But understanding exactly how tidal forces transform chaotic motion into perfect synchronization requires a closer look. A closer look at gravity, at energy, at the long and patient evolution of planetary systems. Because the still face of the moon is not simply a coincidence. It is the visible outcome of a deep physical process, a process that unfolds slowly, silently, and repeatedly across the solar system. And once we begin to follow that process, the pattern becomes impossible to ignore. Moons turning, planets pulling, energy dissipating over millions and billions of years, until motion settles into harmony. So the next time the moon rises above the horizon and that familiar face appears once more in the night sky, it is worth remembering something remarkable. You are not just looking at Earth's companion, you are seeing one example of a cosmic pattern, a pattern that repeats again and again among the world's orbiting distant planets. Which brings us to the central mystery of this story. If so many moons across the solar system show only one face to their planets, then what is the underlying mechanism that makes this happen? Why does gravity seem to guide these worlds toward the same quiet alignment? And how does a spinning moon gradually transform into a perfectly synchronized partner in an orbital dance? To answer those questions, we need to begin where this story first becomes clear, with the moon itself, and with the slow gravitational forces that shaped its motion long ago. To understand why so many moons show only one face to their planets, it helps to begin with the example we know best, our own moon. Every month, the moon completes a journey around Earth. This journey takes about 27.3 days to finish. Astronomers call this the sidereal orbital period, the time required for the moon to travel once around Earth relative to the distant stars. During those 27 days, the moon moves through space along a wide circular path, nearly 770,000 kilometers in diameter. And as it travels along that path, something equally important is happening. The moon is also rotating, slowly, almost imperceptibly. If we could watch the moon from far away in space, we would see it turning gradually as it orbits Earth. But the key detail is this. The moon completes one full rotation in almost exactly the same amount of time it completes one orbit. About 27.3 days. One rotation, one orbit. The two motions remain synchronized. This equality is the reason we always see the same side of the moon from Earth. Because as the moon travels around our planet, it turns just enough to keep the same hemisphere pointed inwards. Imagine standing in the center of a circular room. Now imagine someone walking slowly around you in a circle. If that person keeps their face turned toward you the entire time, they must rotate gradually as they walk. Otherwise, their back would eventually face you. The Moon behaves in exactly this way. As it circles Earth, it rotates at just the right speed to keep one side facing our planet. To observers on Earth, this creates the illusion that the Moon does not rotate at all. But that illusion exists only because the rotation and orbit are perfectly matched. From space, the truth becomes clearer. The Moon is turning continuously, just very slowly. This synchronized motion is what astronomers describe as tidal locking, and once it happens, it creates a very stable arrangement. One hemisphere of the Moon becomes the near side, permanently facing Earth. The opposite hemisphere becomes the far side, always turned away from us. For most of human history, that far side remained completely hidden. No telescope from Earth could ever see it. No matter how long people observed the Moon, the same features always remained in view. Only in 1959, when the Soviet spacecraft Luna 3 flew behind the Moon and photographed its hidden hemisphere, did humanity finally glimpse that unseen landscape. The images revealed a surface very different from the familiar near side. There were far fewer dark basalt plains, many more craters, a rougher and more ancient terrain. For centuries, that entire hemisphere had remained invisible to us, simply because the Moon never rotated to reveal it. Tidal locking had quietly kept it hidden. But the most remarkable aspect of this arrangement is not just the existence of the far side, it is the precision of the synchronization itself. For tidal locking to occur, the Moon's rotation must match its orbital motion almost perfectly. If the Moon rotated even slightly faster than its orbit, we would gradually see different longitudes appear over time. If it rotated slightly slower, the same thing would happen in the opposite direction. Yet the Moon's spin remains extremely close to perfect synchronization, one turn per orbit, a balance maintained over billions of years. In reality, the alignment is not absolutely perfect. Because the Moon's orbit around Earth is slightly elliptical rather than perfectly circular, this causes small variations in the Moon's speed as it travels along its orbit. Sometimes it moves a little faster, sometimes a little slower. These subtle variations allow observers on Earth to glimpse slightly beyond the usual edge of the Moon's near side. This effect is known as libration. Because of libration, we can actually see about 59% of the Moon's total surface from Earth over time, rather than exactly 50%. Even so, the basic pattern remains the same. One hemisphere faces Earth almost all the time. The other remains mostly hidden. The reason this synchronization works so well is that the Moon's rotation and orbit are connected by gravity. The gravitational pull between Earth and the Moon shapes their motion continuously. Over immense spans of time, this interaction gradually slowed the Moon's original rotation until it matched the orbital period we observe today. Once the two periods became equal, the system reached a stable equilibrium. The tidal forces that once slowed the Moon's spin now keep it aligned. This stable configuration is why the same lunar landscapes have remained visible throughout recorded history. The same maria observed by early astronomers. The same craters mapped by telescopes centuries ago. The same mountains photographed by modern spacecraft. The Moon appears almost timeless because its orientation relative to Earth hardly changes. Yet, beneath that apparent stillness lies a carefully balanced motion. Orbit and rotation locked together. A quiet gravitational rhythm repeating every 27 days. For a long time, Scientists wondered whether this arrangement might be unique to our moon. Perhaps the Earth-Moon system had formed under special circumstances. Perhaps tidal locking was rare. But as astronomers began studying other planetary systems more closely, a surprising realization emerged. The same synchronized relationship between rotation and orbit appeared again and again. Moons around distant planets were behaving in exactly the same way. And that discovery raised a fascinating possibility. Perhaps the moon was not unusual at all. Perhaps tidal locking was not a rare exception. Perhaps it was simply the natural outcome for many moons orbiting planets. To explore that idea, we need to expand our view beyond the Earth-Moon system and look outward into the rest of the solar system. Because once we do, we begin to see the same quiet pattern appearing again and again around other worlds. If the story ended with our moon, tidal locking might seem like a curious feature of the Earth-Moon system. An interesting coincidence, a special relationship between one planet and one satellite. But the solar system is far larger than the quiet orbit of our moon. Beyond Mars, beyond the wide belt of asteroids, another world dominates the outer planets. Jupiter, the largest planet in the solar system. More than twice as massive as all the other planets combined. A giant sphere of gas and storms spinning rapidly beneath swirling bands of clouds. Around Jupiter, gravity rules an entire miniature planetary system. Dozens of moons circle this enormous planet. Some are small and irregular, captured long ago by Jupiter's powerful gravity. Others are large enough to resemble planets in their own right. Among these are 4 particularly famous moons. They were first observed in 1610 by the astronomer Galileo Galilei, who pointed a small telescope toward Jupiter and noticed 4 tiny points of light moving around the planet night after night. These moons are now known as the Galilean moons. They are called Io, Europa, Ganymede, and Callisto. Each of them is a world with its own landscape, its own history, and its own remarkable characteristics. Yet, despite their differences, these moons share something very familiar. Like our own moon, they keep one face permanently turned toward the planet they orbit. Take Io, the innermost of the 4. Io circles Jupiter once every 42 hours. That is less than 2 Earth days. During that short time, Io completes one full orbit around the giant planet. And just like Earth's moon, Io also rotates exactly once during that orbit. One rotation, one revolution. The same hemisphere always faces Jupiter. To an observer standing on Jupiter, if such a thing were possible, Io would appear to hover in the sky, slowly drifting back and forth, but never turning to reveal a different side. The same volcanic plains would remain in view constantly. Because Io is tidally locked to Jupiter, the effect is even more striking when we consider how active this moon is. Io is the most volcanically active world in the solar system. Its surface is constantly reshaped by eruptions of molten sulfur and lava. Towering plumes rise hundreds of kilometers above the surface. Bright yellow and orange deposits spread across its landscape. And yet, despite all that violent geological activity, Io's rotation remains perfectly synchronized with its orbit, always showing the same face toward Jupiter. The pattern continues with Europa. Europa lies slightly farther from Jupiter than Io. It completes one orbit every 3.5 Earth days. And again, the same relationship appears. Europa rotates once during each orbit. One turn per revolution. The same side, always facing Jupiter. Europa's surface looks very different from Io's fiery terrain. Instead of volcanoes and lava flows, Europa is covered in smooth, pale ice. Long, dark fractures stretch across its surface like cracks in frozen glass. Beneath that frozen shell, scientists believe a vast ocean of liquid water may exist. An ocean potentially deeper than all the oceans on Earth combined. Yet, despite this icy stillness, Europa shares the same rotational rhythm as Io. Orbit and rotation moving together, locked. Then there is Ganymede, the largest moon in the solar system. Ganymede is so large that it actually exceeds the size of the planet Mercury. It has its own magnetic field. Ancient dark terrain covers much of its surface, crossed by lighter bands formed by geological activity long ago. Ganymede takes about 7 days to orbit Jupiter, and just like the others, it rotates once during that time. One face toward Jupiter, the same pattern again. Even Callisto, the outermost of the Galilean moons, follows this rule. Callisto's surface is heavily cratered, one of the oldest and most unchanged landscapes in the solar system. It takes nearly 17 days to complete an orbit around Jupiter, and again, one rotation occurs during that same period. Always the same hemisphere facing inward. When astronomers first realized this, it was an important clue, because here were 4 very different worlds. Io, fiery and volcanic. Europa, icy and fractured. Ganymede, large and magnetized. Callisto, ancient and cratered. Yet, despite these differences, each moon shared the same rotational behavior. Each one was tidally locked. Each one turned once during every orbit around Jupiter. This meant that the phenomenon we observe with our moon was not unique. It was happening elsewhere, repeatedly, across an entirely different planetary system. Jupiter's enormous gravity plays a role in this process. The planet is more than 300 times as massive as Earth, and its gravitational pull strongly influences the motion of its moons. Over long periods of time, tidal forces generated by Jupiter gradually slowed the rotation of these moons, just as Earth's gravity once slowed the spin of our moon. Eventually, the same equilibrium emerged. Rotation and orbit matched. One hemisphere facing inward. The system settling into stability. And once astronomers began looking for this pattern, they started to find it almost everywhere. Many moons throughout the solar system follow the same rule. Orbit once, rotate once, remain locked to the world they circle. This realization slowly transformed our understanding of the moon. Instead of being a rare gravitational curiosity, the Earth-Moon system began to look like part of a much larger pattern. A pattern that repeats wherever a moon orbits close enough to its planet for long enough. But Jupiter is only one example. Farther out in the solar system, another giant planet hosts an even larger family of moons. A planet famous for its brilliant rings and its mysterious satellites. Saturn. And among Saturn's many moons lies one of the most intriguing worlds we have ever discovered. A world wrapped in a thick orange atmosphere. A moon with rivers, lakes and rain, though not of water. A moon that also follows the same quiet gravitational rhythm. Because, like Earth's moon, and like the moons of Jupiter, this distant world is also tidally locked to its planet. Its name is Titan, and its story reveals just how widespread this cosmic pattern truly is. Beyond the orbit of Jupiter, farther into the colder regions of the solar system, another giant planet travels slowly around the Sun. Saturn. From a distance, Saturn appears serene. Its wide rings stretch across space like delicate bands of light. Countless particles of ice and rock circle the planet in a thin, shimmering disk. But Saturn is not alone. Like Jupiter, it possesses a vast family of moons. More than 80 have been discovered so far, worlds ranging from tiny, irregular fragments to large, complex bodies with landscapes shaped by ice, geology, and time. Among them, one moon stands out immediately. The largest of Saturn's satellites, a world so large that it exceeds the planet Mercury in diameter. Its name is Titan. Titan is unlike any other moon in the solar system. When early astronomers first observed it through telescopes, they noticed something unusual. Unlike most moons, Titan appeared slightly blurred. Not because of poor optics, but because the moon itself was hidden beneath a thick atmosphere. Later spacecraft would confirm what those early observations hinted at. Titan possesses a dense envelope of gas, an atmosphere composed primarily of nitrogen mixed with methane and other organic molecules. The atmosphere is so thick that the surface cannot be seen clearly from space using ordinary visible light. Instead, Titan appears wrapped in a permanent orange haze. Sunlight passing through this haze is scattered and absorbed, producing the soft, amber glow that has become Titan's signature appearance. Beneath those clouds lies an extraordinary landscape. Rivers carved into the ground, lakes gathered in shallow basins, occasional rainfall falling from the sky. But unlike Earth, where water shapes these features, Titan's rivers and lakes are made of liquid methane and ethane. At Titan's surface temperature, around -180 degrees Celsius, these hydrocarbons behave much like water does on Earth. They flow, they collect, they evaporate and condense in a slow atmospheric cycle. Titan, in many ways, resembles a distant and frozen mirror of Earth's own hydrological systems. Yet despite its alien weather and distant orbit, Titan shares a very familiar relationship with the planet it circles. Because Titan, like many moons before it, is tidally locked. Titan completes one orbit around Saturn approximately every 16 Earth days. During that time, it also completes one rotation on its axis. One orbit, one rotation. The same quiet synchronization we observed earlier. As Titan travels along its wide path around Saturn, it turns just enough to keep one hemisphere facing the giant planet at all times. To an observer standing on Saturn, if such a vantage point were possible, Titan would appear almost motionless in the sky. It would drift slowly across the background of stars, but its surface orientation would never change. The same methane lakes, the same continents of icy rock, the same cloud patterns drifting through Titan's thick atmosphere. Always the same side facing Saturn. Always the same orientation maintained through time. This discovery reinforced a growing realization among planetary scientists. The pattern seen with Earth's moon and with the moons of Jupiter was appearing again around Saturn. Different planet, different distance from the Sun, different moon, yet the same rotational behavior. Titan's environment could hardly be more different from that of Io or Europa. Its thick atmosphere shields its surface from the vacuum of space. Its rivers and lakes are formed from hydrocarbons rather than water. Its weather patterns move slowly through a hazy sky, and yet gravity has guided Titan into the same stable rotational configuration, one face turned inward toward Saturn, forever. Observations from spacecraft provided clear evidence of this alignment. When the Cassini-Huygens spacecraft entered orbit around Saturn in 2004, it began studying Titan in extraordinary detail. Radar instruments were able to penetrate Titan's thick clouds and map its surface. As the spacecraft repeatedly flew past Titan over many years, scientists noticed something important. Each time Titan completed an orbit around Saturn, the same regions of the Moon faced the planet again. Its orientation remained fixed relative to Saturn. Orbit and rotation remained perfectly synchronized, just as they were for Earth's moon, just as they were for the moons of Jupiter. This repetition was no longer easy to dismiss as coincidence. Here were multiple planetary systems, each containing moons with very different sizes, compositions, and environments. Yet again and again, those moons ended up in the same rotational state. One rotation per orbit, one hemisphere permanently facing the planet they orbit. A pattern repeating itself across the solar system. The more examples astronomers discovered, the clearer the implication became. This behavior was not the result of a unique accident. It was the natural outcome of gravitational physics. Some process, quiet, gradual, and persistent, was guiding moons toward this shared alignment. A process capable of acting across billions of years, slowly adjusting the spin of entire worlds until their rotation matched their orbital motion. The repeated appearance of tidal locking around both Jupiter and Saturn hinted at something deeper, a universal mechanism operating wherever a moon orbits a planet closely enough for long enough. But what exactly was happening? What invisible influence could gradually reshape the rotation of a moon? How could gravity, acting from far away, slowly slow the spin of a world until it synchronized perfectly with its orbit? The answer lies in a subtle effect that operates throughout planetary systems. A gentle but persistent force created by tidal interactions between two bodies. It is the same process that raises ocean tides on Earth. But when applied to entire moons and planets, its influence becomes far more profound. Because tidal forces do more than lift oceans, they stretch solid worlds. They generate heat inside planetary interiors, and over immense spans of time, they can reshape motion itself. To understand why moons like our own moon, Io, Europa, and Titan all end up showing one face to their planets, we now need to look more closely at this process, at the slow gravitational stretching known as tidal forces, and at the subtle friction that gradually transforms chaotic rotation into perfect synchronization. By this point, a pattern has begun to emerge. Earth's moon shows only one face to our planet. Several moons of Jupiter do the same, and far away, orbiting Saturn, the moon, Titan, follows the very same rule. Different worlds, different environments, yet the same quiet alignment appears again and again. One orbit, one rotation, one hemisphere always facing the planet. At first glance, this might seem almost mysterious, but beneath these repeating examples lies a physical mechanism that scientists now understand quite well. A mechanism driven by gravity, more specifically, by tidal forces. To see how this works, it helps to imagine a moon orbiting its planet long before tidal locking occurs. In the early stages of its history, the moon might rotate freely. Its days and nights sweep rapidly across the surface as it spins through space. But the planet it orbits exerts a powerful gravitational pull, and that pull is not perfectly uniform. The side of the moon that faces the planet experiences a slightly stronger gravitational attraction. The far side feels a slightly weaker pull. This difference may seem tiny, but across an entire world, even a small imbalance in gravity can have noticeable effects. Instead of remaining perfectly spherical, the moon becomes very slightly stretched. the shape of the moon elongates along the line pointing toward the planet. Astronomers call this distortion a tidal bulge. One bulge forms on the side facing the planet, another forms on the opposite side. In effect, the moon becomes just a little bit oval, rather than perfectly round. If the moon were made entirely of fluid, like an ocean or a gas cloud, this stretching would happen very easily. But moons are mostly solid rock and ice. They resist deformation. So the tidal bulge is extremely small, often only a few meters high, across a world thousands of kilometers in diameter. Yet even this tiny distortion matters, because the moon is still rotating. And if its rotation does not perfectly match its orbital motion, the tidal bulge will not point directly toward the planet. Instead, it will be slightly shifted. Imagine the moon rotating faster than it orbits. In that case, the bulge will be carried a little ahead of the line connecting the moon and the planet. The moon's rotation drags the bulge forward, but gravity does not ignore this displacement. The planet's gravity continues to pull on the bulge, and because the bulge is now slightly ahead of the planet-moon line, that gravitational pull produces a torque, a gentle twisting force. This torque acts to slow the moon's rotation. Little by little, it removes energy from the spinning motion. Over time, the moon's rotation gradually decreases. But where does that lost energy go? It does not simply vanish. Instead, it is converted into heat. Inside the moon, the constant stretching and flexing caused by tidal forces generates friction. The rock and ice within the moon deform slightly as the tidal bulge shifts position. Those tiny movements produce internal friction, and that friction warms the moon's interior. The process is slow, extremely slow, but it never stops. Every orbit, the moon flexes just a little. Every rotation, internal friction drains a tiny amount of rotational energy, and over immense spans of time, the effect becomes significant. The moon's spin continues to slow, gradually, patiently, until eventually something remarkable happens. The moon's rotation slows enough that it begins to match its orbital period. When that moment arrives, the tidal bulge stops shifting. It lines up directly with the planet. One bulge pointing toward the planet, the other pointing directly away. Now, the planet's gravity pulls symmetrically on the bulges. No torque is produced. No further slowing occurs. The system has reached a stable equilibrium. The moon's rotation now matches its orbit perfectly. From that moment forward, the same hemisphere of the moon always faces the planet. Tidal locking has occurred. The once freely spinning world has become synchronized with its orbit. A stable gravitational arrangement has emerged. And once established, this state can persist for billions of years. This mechanism explains why so many moons across the solar system share the same rotational behavior. Any moon orbiting close enough to a large planet will experience tidal forces. Given enough time, those forces gradually reshape its rotation, slowly removing energy from its spin, gradually guiding the moon towards synchronization. The process does not require unusual conditions. It simply requires time. Time for gravity to stretch the moon. Time for internal friction to dissipate energy. Time for the moon's rotation to settle into balance with its orbit. And because many moons have existed for billions of years, tidal locking has had ample opportunity to occur. That is why we observe it so frequently. Earth's moon, the moons of Jupiter, the moons of Saturn. World after world, quietly settling into the same gravitational rhythm. Yet there is another important part of this story. The process we have just described does not happen quickly. It unfolds over immense spans of time. Millions of years, hundreds of millions, sometimes billions. The transformation from a rapidly spinning young moon into a tidally locked world is one of the slowest changes in planetary evolution. To truly understand why tidal locking is so common, we must consider these extraordinary timescales. Because the quiet gravitational forces that reshape a moon's rotation are patient. They act slowly, but relentlessly across the deep history of the solar system. And it is within those vast stretches of time that spinning worlds gradually settle into the calm alignment we observe today. The mechanism behind tidal locking is not violent. It does not act suddenly. There are no collisions, no dramatic shifts in motion, no abrupt transformations. Instead, the process unfolds with extraordinary patience. Gravity stretches a moon slightly. Internal friction converts a tiny amount of rotational energy into heat. The moon's spin slows just a little. Then the process repeats, again and again. Each orbit contributes only the smallest change, a fraction of a degree in rotational speed. A shift so subtle that no observer watching for a single year or even 1,000 years would notice anything at all. Yet across the immense timescales of the solar system, these tiny changes accumulate. To understand this, we need to return to the early history of moons themselves. When moons first form, they rarely begin in a synchronized state. Instead, they tend to rotate quickly. In the chaotic environment where planets and moons assemble, through collisions, accretion, and gravitational interactions, newly formed bodies often inherit rapid spins. A young moon may rotate many times during a single orbit around its planet. Day and night sweep across its surface repeatedly. The sky shifts constantly. The planet it orbits appears to rise and set like a wandering star. In those early stages, the moon behaves much like a small planet, freely spinning, unconstrained. But even then, tidal forces are already at work. The nearby planet begins exerting its uneven gravitational pull. The side of the moon closest to the planet feels a stronger attraction. The far side feels slightly less. That difference stretches the moon ever so slightly along the line pointing toward the planet. The tidal bulge forms, and if the moon rotates faster than its orbital motion, the bulge drifts out of alignment. Gravity responds by applying torque. The moon's spin begins to slow. At first, the change is extremely small. So small that millions of years may pass before the difference becomes measurable. But time in the solar system is abundant. Planets and moons do not exist for mere centuries or millennia. They persist for billions of years. Within such enormous stretches of time, even the gentlest physical processes can reshape entire worlds. Every orbit contributes a tiny loss of rotational energy. Every tidal flexing event warms the moon's interior slightly. The energy removed from the moon's spin is slowly converted into heat within its crust and mantle. The moon's rotation continues to slow. Gradually, steadily, almost imperceptibly. Imagine watching a spinning globe on a table. At first, it turns quickly. But with each passing moment, friction with the surface beneath it slows the motion just a little. Eventually, the globe rotates more slowly, then more slowly still, until finally it comes to rest. Tidal locking operates in a similar way, except the friction occurs deep inside the moon, caused by tidal stretching rather than contact with the surface, and the timescale is vastly longer. For many moons, the full process takes hundreds of millions to billions of years. For example, Earth's own moon is thought to have become tidally locked relatively early in its history, within the first several hundred million years after its formation. During that time, tidal forces between Earth and Moon gradually slowed the Moon's rotation until it matched its orbital period. Once synchronization occurred, the system settled into the stable configuration we observe today. But this outcome was not inevitable in the beginning. It emerged slowly from the quiet influence of gravitational forces acting across deep time. The same story likely unfolded for many other moons. Around Jupiter, the large moons, such as Io, experience strong tidal forces due to the immense mass of their parent planet. These forces accelerate the synchronization process. Over time, their rotations slowed and eventually aligned with their orbits. The same occurred around Saturn, where moons like Titan gradually settled into the same gravitational balance. What once appeared as a mysterious coincidence now begins to look more like a natural outcome of long-term evolution. Given enough time, tidal forces guide many moons towards synchronization, not because the universe prefers stillness, but because this configuration minimizes the ongoing distortion caused by gravity. Once the tidal bulge aligns directly with the planet, the twisting torque disappears. Energy loss stops. The system becomes stable, and stability tends to persist. In this sense, tidal locking represents a kind of gravitational resting point, a state toward which many moon-planet systems slowly drift. This perspective helps explain why the phenomenon appears so frequently. Across the solar system, moons have existed for billions of years. That span of time is more than sufficient for tidal forces to reshape their rotations. What we observe today is therefore not a collection of unusual coincidences. It is the accumulated result of billions of years of quiet gravitational adjustment. Worlds slowly synchronizing with the planets they orbit. Spinning moons gradually settling into calm alignment. And once this alignment is achieved, it becomes remarkably persistent. The same face remains turned toward the planet, orbit after orbit, year after year, epoch after epoch. From the outside, the moon appears almost motionless. Yet that stillness is the product of immense time and subtle forces working together. Gravity stretching, friction dissipating energy, rotation gradually slowing, until at last, motion and orbit become one and the same. The repeating examples we have seen, from Earth's moon to the moons of Jupiter and Saturn, are not isolated curiosities. They are visible traces of a deeper pattern, a reminder that even slow and gentle forces can shape the architecture of planetary systems when given enough time. And once we recognize that pattern, a new perspective begins to emerge. The synchronized moons scattered throughout the solar system are not merely similar cases of the same physics. Together, they reveal something about how gravitational systems naturally organize themselves. A quiet tendency toward balance, a repeated movement towards stable configurations. And it is this deeper meaning, this broader harmony in the motions of worlds, that we will now begin to explore. When we look up at the moon today, its behavior feels permanent. The same familiar craters appear night after night. The same dark plains drift slowly across the sky as the moon rises and sets. For an entire human lifetime, nothing seems to change. It is easy to imagine that the moon has always been this way. Quiet, predictable, forever showing the same face to Earth. But this calm arrangement was not the moon's original state. Long before the moon settled into its present rhythm, it likely behaved very differently. To understand that earlier time, we need to travel back to the early history of the solar system. More than 4 billion years ago, a time when planets were still forming and the architecture of the solar system was far less orderly than it appears today. During that distant era, moons did not begin their lives in perfect synchronization. Instead, they lightly spun freely. Young moons were born from chaotic events. Some formed from the debris of giant impacts. Others condensed from swirling disks of gas and dust around newly formed planets. In these turbulent environments, motion was rarely gentle or balanced. Collisions transferred momentum. Gravitational encounters nudged objects into new orbits. Fragments merged together to form larger bodies. Through these processes, a newborn moon could easily acquire a rapid spin. Its rotation might have been much faster than the time it took to orbit its planet. If we could have watched the moon during those early stages, the sky above its surface might have looked very different. Earth would not have remained fixed in the same position. Instead, the planet would slowly drift across the lunar sky, rising above one horizon, crossing overhead, and setting again. Each lunar day might have looked different from the last. The moon would have behaved like a small rotating world, much like Earth itself, day and night sweeping repeatedly across its surface. But even in those early moments, gravity was already shaping the future. The nearby presence of Earth meant that tidal forces were constantly stretching the young moon. The gravitational pull on the moon's near side was slightly stronger than the pull on its far side. This difference created the tidal bulges we explored earlier. At first, those bulges did not align perfectly with Earth. Because the moon was spinning faster than it orbited, the bulges drifted ahead of the Earth-Moon line. And that small misalignment allowed gravity to begin its quiet work. The torque created by Earth's pull slowly resisted the moon's rotation. Each orbit drained a tiny fraction of rotational energy. Inside the moon, the constant stretching and flexing produced internal friction. That friction converted rotational motion into heat. The moon's spin began to slow. Not dramatically, not suddenly, but steadily, over millions of years. Then hundreds of millions. Eventually, the difference between the moon's spin and its orbital motion began to shrink. The moon rotated more slowly. The tidal bulges drifted less. The torque weakened as the system moved closer to balance. And finally, after immense stretches of time, the moon reached the configuration we observe today. One rotation every orbit. One hemisphere always facing Earth. Synchronization. When viewed from this perspective, tidal locking is not a strange quirk of a single moon. It is the natural endpoint of a long evolutionary process. A transformation from random motion to ordered motion. At the beginning, the system contains many possibilities. A moon might spin rapidly. It might rotate slowly. Its orientation might change constantly relative to the planet it orbits. But over time, tidal forces gradually narrow those possibilities. They remove energy from the system. They guide the moon toward a configuration where the tidal bulges no longer shift, where gravitational torque disappears, where motion becomes stable. This transition is subtle. There is no single moment when the universe declares that synchronization has been achieved. Instead, the system slowly drifts toward equilibrium. The moon's rotation becomes more and more closely matched to its orbit, until eventually the difference becomes zero. And once that happens, the configuration tends to persist. The same story likely unfolded many times throughout the solar system. Around Jupiter, moons such as Io probably began with their own independent rotations. Over time, tidal forces from Jupiter gradually slowed those spins. Eventually, their rotations synchronized with their orbits. Around Saturn, the moon Titan likely experienced a similar journey. From a freely spinning world to one whose orientation is now permanently fixed relative to its planet. What we observe today is therefore the final chapter of a very long story. A story written slowly by gravity. The familiar stillness of tidally locked moons is not the beginning of that story. It is the result of billions of years of gradual adjustment. Motion becoming organized. Chaos settling into balance. Worlds quietly aligning themselves with the planets they orbit. And once we recognize this transformation, another insight begins to emerge. Synchronization does not simply happen because tidal forces slow rotation. It happens because this configuration represents something deeper, a state of maximum stability, a gravitational arrangement in which energy loss stops and the system can remain unchanged for immense periods of time. Understanding that stability will reveal why tidal locking appears so often throughout the solar system, and why so many moons, despite their differences, ultimately arrive at the same quiet alignment. As we have seen, tidal locking is not something that happens suddenly. It emerges slowly. A moon begins with free rotation. Tidal forces stretch its shape. Internal friction converts a small portion of its rotational motion into heat. Bit by bit, the spin slows. But this raises an important question. Why does the process stop at exactly one rotation per orbit? Why does the system settle there and not somewhere else? The answer lies in a simple but powerful principle that appears throughout physics. Systems tend to move towards states with lower energy. Not instantly, not deliberately, but gradually, through the quiet removal of excess motion. When we drop a stone, it falls downward because the lower position represents a state of lower gravitational energy. When a stretched spring is released, it relaxes back to its natural length because that configuration contains less stored energy. In the same way, a rotating moon orbiting a planet contains more energy than it ultimately needs, and tidal forces provide a slow pathway for that energy to be released. At first, when a moon rotates faster than it orbits, the tidal bulge does not line up perfectly with the planet. Instead, the bulge is carried slightly ahead by the moon's rotation. This misalignment matters, because the planet's gravity pulls strongly on that stretched region of the moon, and since the bulge is offset from the direct planet-moon line, the gravitational pull produces torque. That torque acts like a gentle brake on the moon's spin. Each orbit removes a small amount of rotational energy. Inside the moon, the constant flexing of rock or ice produces internal friction. That friction warms the interior slightly. Energy that once belonged to the moon's spin becomes heat. The moon rotates more slowly. But as the spin slows, something subtle begins to change. The tidal bulge drifts closer to alignment with the planet. The offset becomes smaller. The torque weakens. Energy loss continues, but at a slightly reduced rate. And eventually, the system approaches a special configuration. A moment when the moon rotates exactly once during each orbit. At that point, something remarkable happens. The tidal bulge no longer shifts. It points directly toward the planet. And because the bulge is perfectly aligned, the planet's gravity pulls symmetrically on it. There is no sideways component of force, no twisting torque, no mechanism left to slow the moon's rotation further. The process that once removed energy now stops. The system has reached equilibrium. This synchronized state represents the minimum energy configuration for the moon's rotation relative to its orbit. Any faster spin would push the bulge ahead again, creating torque that slows the moon down. Any slower spin would cause the bulge to fall behind, allowing torque to speed the rotation back up. In either case, gravity nudges the system back towards the synchronized state. The alignment becomes self-correcting, stable. And because energy is no longer being dissipated through tidal friction, the configuration can persist for extraordinary lengths of time. Once tidal locking occurs, it tends to last for billions of years. This explains why we observe the same arrangement across so many moons. Earth's familiar companion, Moon, has remained tidally locked to Earth for most of its history. Around the giant planet Jupiter, moons like Io also rotate once per orbit. And far beyond, orbiting Saturn, the large moon Titan maintains the same gravitational alignment. Different worlds, different environments, yet the same endpoint appears again and again. Not because these moons are copying one another, but because the laws of physics guide them toward the same stable solution. In this sense, tidal locking is less like a rare phenomenon and more like a gravitational resting point. A natural outcome for moons that orbit close enough to their planets for tidal forces to matter. Over time, energy drains away, motion becomes simpler, until finally the moon settles into the calmest configuration available. One rotation, one orbit. Perfect synchronization. When we look at the sky and see the moon's unchanging face, we are not witnessing stillness in the ordinary sense. We are seeing the end result of a long search for equilibrium. Billions of years of tiny adjustments, gravity stretching, friction dissipating energy, rotation gradually slowing until balance is achieved. And once that balance is reached, the system remains quietly stable. The same hemisphere faces the planet, orbit after orbit, century after century, eon after eon. Understanding this principle changes how we interpret the repeating examples scattered across the solar system. They are not coincidences. They are expressions of the same underlying tendency toward stability, a pattern written into the physics of gravity itself. And when we step back to view the solar system as a whole, this pattern becomes even more striking. Moons around different planets, worlds separated by hundreds of millions of kilometers. Yet many of them share the same gravitational alignment, the same quiet equilibrium. Which leads to a deeper realization. Tidal locking is not merely something that happened to our moon. It is part of a much broader structure, shaping the motions of moons throughout the solar system. At the beginning of this journey, we started with something familiar, the quiet image of the moon rising in Earth's night sky. For as long as humans have watched it, the same patterns of craters and plains have faced us, the same bright highlands, the same dark lunar seas, night after night, generation after generation. That view has remained almost unchanged. It can feel as though this behavior belongs uniquely to our moon, a small peculiarity of the Earth-Moon system. But now, that impression begins to dissolve. Because once we step back and look across the solar system, a much larger pattern becomes visible. The moon is not unusual. It is simply one member of a much broader family of synchronized worlds. To see this clearly, we can begin by looking outward again. Far beyond the orbit of Earth lies Jupiter, the largest planet in the solar system. Jupiter is surrounded by a vast retinue of moons. Some are small and irregular, others are large enough to resemble miniature planets. Among them are several remarkable worlds, first observed by Galileo Galilei in 1610. When Galileo pointed his telescope toward Jupiter, he saw tiny points of light moving beside the planet. Night after night, their positions changed. They were not distant stars. They were moons, worlds orbiting another world. This discovery quietly transformed humanity's view of the universe. Not everything revolved around Earth. Other centers of motion existed, other gravitational systems. One of these moons is Io. Io is one of the most geologically active places in the solar system. Its surface is covered with hundreds of volcanoes. Some eruptions send plumes of gas and dust hundreds of kilometers into space. Sulfur compounds color the landscape in shades of yellow, orange, and red. Io is constantly reshaping itself, but beneath all that volcanic chaos, its motion follows a very quiet rule. Io rotates exactly once during each orbit around Jupiter. One spin, one orbit, always the same hemisphere facing the planet, the same alignment maintained year after year. Another moon travels nearby, Europa. Europa looks very different from Io. Its surface is smooth and pale. A shell of ice covers the entire moon. Long cracks stretch across the frozen plains like dark veins. Scientists believe a vast ocean lies hidden beneath this ice, an ocean possibly containing more water than all of Earth's seas combined. And yet, despite this icy surface and hidden ocean, Europa shares the same gravitational rhythm. One orbit, one rotation. The same hemisphere, always facing Jupiter. Another tidally locked world. Farther outwards still orbits Ganymede. Ganymede is enormous. It is the largest moon in the entire solar system, larger even than the planet Mercury. Its surface contains two distinct landscapes, ancient dark regions scarred by countless impacts, and younger bright terrain, marked by long grooves carved by tectonic forces long ago. Ganymede even possesses its own magnetic field, a rare feature for a moon. And yet, despite its size and complexity, Ganymede follows the same rule. One rotation, one orbit. The same face always turned toward Jupiter. When we step back and look at Jupiter's system as a whole, the pattern becomes unmistakable. Multiple moons, different sizes, different compositions, different histories. And yet, the same rotational outcome appears again and again. Tidal locking. Not once, not twice, but repeatedly. Now, let us move farther outward. Beyond Jupiter lies Saturn. Saturn is surrounded by its magnificent rings. But beyond those rings circles another large population of moons. Among them is one of the most fascinating worlds in the solar system, Titan. Titan is wrapped in a thick orange atmosphere. Clouds drift slowly through its sky. Rain falls. Rivers carve channels through the landscape. Lakes gather in shallow basins. But these lakes are not made of water. They are composed of liquid methane and ethane. At Titan's surface temperature, around -180 degrees Celsius, these hydrocarbons behave like water does on Earth. They flow, they evaporate, they fall again as rain. Titan possesses an entire weather system, an alien hydrological cycle. Yet despite its strange climate and thick atmosphere, Titan shares the same quiet orbital behavior we have seen elsewhere. It rotates once during each orbit around Saturn, one hemisphere always facing the planet. Another example of tidal locking. And Titan is not Many other moons of Saturn follow the same gravitational pattern. across the solar system, wherever moons orbit close enough to their planets, tidal forces slowly reshape their motion. Rotation slows, energy dissipates, alignment emerges. By now, the pattern becomes difficult to ignore. Earth's moon, the moons of Jupiter, the moons of Saturn. Different worlds, different environments, and yet the same final arrangement appears again and again. What once seemed like coincidence now reveals itself as something else entirely, a natural outcome of gravitational evolution. Gravity acts patiently. Internal friction removes energy slowly but steadily. Given enough time, motion becomes simpler. Spinning worlds gradually settle into calm alignment, until finally they reach the configuration where tidal forces no longer twist their rotation. A state of balance, a state of stability. One orbit, one rotation. Perfect synchronization. When we look up at the moon now, its still face takes on a new meaning. We are not witnessing something rare, we are witnessing a pattern repeated across planetary systems, world after world, quietly settling into the same gravitational rhythm. And once we recognize this pattern among moons, another question begins to appear. If tidal locking is so common between moons and planets, could the same thing happen elsewhere? Could entire planets become locked to the stars they orbit? Could there be worlds where one side faces a sun forever, while the other remains in eternal night? This possibility leads the story beyond our solar system, because the same laws of gravity apply everywhere. Moons around planets, planets around stars. Across the universe, gravitational systems slowly evolve toward balance, and tidal locking may be one of the most common outcomes of that long evolution. The still face of our moon, once seen as a simple curiosity, is actually part of a vast cosmic pattern. A quiet signature of gravity organizing motion across billions of years. A reminder that even the gentlest forces, given enough time, can shape the motions of entire worlds. For most of this story, tidal locking has sounded like an ending, a moment when motion finally settles, when the rotation of a moon matches its orbit and the system reaches equilibrium. The same face toward the planet, orbit after orbit, stable, balanced, unchanging. But the truth is a little more subtle, because even after tidal locking occurs, gravity does not stop working. The Earth-Moon system is still evolving, slowly, quietly, almost invisibly. Every day, Earth rotates once on its axis. This rotation is so familiar that it feels permanent. Day follows night, night follows day. The rhythm repeats with reassuring regularity. Yet Earth's rotation is not perfectly constant. It is gradually slowing. The change is incredibly small, but it is real. And the cause, once again, is gravity. More specifically, tidal forces between Earth and the Moon. To see why this happens, imagine the oceans of Earth responding to the Moon's gravitational pull. The side of Earth closest to the Moon feels a slightly stronger attraction. Water is pulled outward, forming a tidal bulge. On the opposite side of the planet, another bulge forms. These ocean tides rise and fall across the globe. Twice each day, coastlines around the world experience the steady breathing of the sea. But Earth is rotating, and because of this rotation, the tidal bulges do not remain perfectly aligned with the Moon. They are dragged slightly ahead. Earth spins faster than the Moon orbits, so the ocean bulges move a little in front of the Earth-Moon line. Just a little, but enough to matter. The Moon's gravity pulls on those displaced bulges, and because they are slightly ahead of the Moon's position, that gravitational pull produces torque, a gentle braking force. it slows Earth's rotation. Not dramatically, but steadily. Tiny amounts of rotational energy are removed from Earth's spin. The process is incredibly slow. On average, Earth's day grows longer by about 2 milliseconds every century, 2/1000ths of a second. So small that no human life could ever notice the difference. Yet across millions of years, the change becomes meaningful. Hundreds of millions of years ago, Earth's days were shorter, long before dinosaurs appeared. A day may have lasted only about 22 hours. Go back even farther, and Earth spun faster still. The slowing continues today. Gravity is still quietly adjusting the motion of our planet, but the energy removed from Earth's rotation does not disappear. It must go somewhere, and the destination of that energy is the Moon's orbit. As Earth loses rotational energy, the Moon gains orbital energy. The result is subtle but measurable. The Moon slowly moves farther away from Earth. Every year, the distance increases by about 3.8 centimeters, roughly the width of a human finger. Again, an incredibly small change. Yet this motion has been measured directly using lasers. During the Apollo program, astronauts placed reflective mirrors on the lunar surface. Scientists on Earth can send laser pulses toward those mirrors. The light reflects back. By measuring how long the light takes to return, researchers can determine the distance to the Moon with extraordinary precision, millimeter accuracy. These measurements reveal something remarkable. The Moon is drifting away, slowly, year after year. This outward migration is part of the same tidal interaction that slowed the Moon's rotation long ago. The system is still exchanging angular momentum. Earth's spin continues to slow. The Moon's orbit slowly expands. The gravitational relationship between the two bodies evolves. Even though the Moon is tidally locked, the story is not finished. To appreciate this, imagine looking far into the future, millions of years from now, then hundreds of millions. Eventually, the Moon will be significantly farther from Earth than it is today. Its orbital period will grow longer. The Moon will take more time to complete each circuit around our planet. Meanwhile, Earth's rotation will continue to slow. Days will gradually lengthen. Night and day will stretch farther apart. The difference will remain tiny within any human lifetime, but across geological time, it accumulates. The rhythm of Earth slowly changes. If this process were allowed to continue indefinitely, the system would eventually approach another equilibrium, a distant future configuration. In that final state, Earth would rotate once during the same time the Moon completes one orbit. Just as the Moon currently shows only one face to Earth, Earth would also show only one face to the Moon. Both bodies would be tidally locked to each other. The Moon would remain fixed above one region of Earth's surface, always hanging in the same part of the sky, never rising, never setting. From one hemisphere of Earth, the Moon would appear permanently overhead. From the opposite hemisphere, it would never be visible at all. A perfectly synchronized pair of worlds. However, this ultimate state lies far beyond the timescale of our civilization. It would require tens of billions of years, longer than the remaining lifetime of the Sun itself. In reality, the Sun will evolve into a red giant long before that final equilibrium is reached. The Earth-Moon system will likely change dramatically during that distant era, but the important insight remains. Even now, in the present moment, the system continues to evolve. Tidal locking was not the end of the story. It was simply one chapter. When we look up at the Moon tonight, its still face might appear timeless. The same craters, the same pale plains, unchanging. Yet behind that calm appearance, subtle changes continue. Earth's rotation slowing, the moon drifting outward, angular momentum flowing through the system, gravity quietly redistributing motion. The Earth-Moon system is not frozen, it is evolving. Slowly, gracefully, across immense spans of time. Seen from this perspective, tidal locking becomes something richer than a static arrangement. It is part of a long gravitational conversation between two worlds. A conversation measured not in days or centuries, but in millions and billions of years. Each tidal interaction transfers a tiny piece of energy. Each orbit nudges the system toward new configurations. The present alignment, Moon locked to Earth, is simply the stage we happen to observe today. A moment within a much longer evolution. And this realization changes how we understand the Moon's familiar face. The stillness we see is not absolute. It is the visible expression of deeper motion. Subtle forces at work beneath the surface of time. Gravity stretching oceans, friction warming interiors, angular momentum shifting between worlds. Even now, the solar system is not finished arranging itself. It is still settling, still evolving, still seeking balance. The Moon, quietly circling above our planet, carries the memory of that long gravitational history. Its synchronized rotation tells the story of tidal forces acting across billions of years. And the slow widening of its orbit reminds us that the process continues, quietly, patiently, almost imperceptibly. In this way, the Earth-Moon system becomes more than just a pair of celestial bodies. It becomes a living example of gravitational evolution. A reminder that cosmic systems rarely stand still. They move, they adjust, they drift toward new equilibria over immense stretches of time. And once we see the Moon through this lens, the night sky feels slightly different. The familiar lunar face is no longer just a static object in the sky. It is a moment in a much larger story. A story written by gravity. A story unfolding slowly across billions of years. A story that continues, quietly, even tonight. At the beginning of this journey, we asked a simple question. Why does the Moon always show the same face to Earth? For most of human history, that question had no clear answer. The Moon simply appeared, still, night after night, century after century. The same craters, the same shadows, the same pale surface looking back at us. It was easy to imagine that this was a strange coincidence, a peculiar feature of the Earth-Moon system. But step by step, the picture began to change. First, we learned that the Moon is not truly motionless. It rotates. Slowly. One complete rotation every 27.3 days, matching its orbit around Earth. What appears to be stillness is actually perfect synchronization. Then we looked outward into the solar system, and we found that our Moon is not alone. Moons orbiting Jupiter behave the same way. Worlds like Io, Europa, and Ganymede each rotate once during every orbit. The same hemisphere, always facing their planet. Farther out, around Saturn, the large moon Titan follows the same rule. Different worlds, different environments, yet the same gravitational alignment appears again and again. What once seemed rare now looks familiar, a repeating pattern written across planetary systems. Then we explored the physical cause, tidal forces, the gentle stretching created by gravity acting unevenly across a moon. At first, moons rotate freely. Their spin has little connection to their orbit. But tidal interactions slowly reshape that motion. Internal friction removes energy, rotation slows. Bit by bit, orbit after orbit, until eventually the system reaches equilibrium. The tidal bulge aligns with the planet, torque disappears, and the moon settles into synchronization. One orbit, one rotation, a state of balance. Once established, that balance can persist for billions of years. But even then, the story does not stop. The Earth and the Moon continue to exchange energy. Earth's rotation gradually slows. The Moon slowly drifts outward. A quiet evolution still unfolding across geological time. This ongoing motion reminds us that tidal locking is not a frozen state. It is part of a longer gravitational process, a system slowly adjusting itself, seeking stability. When we gather all these pieces together, a deeper realization emerges. The Moon's familiar face is not an accident. It is the natural outcome of gravitational physics. Whenever a moon orbits close enough to a massive planet, whenever tidal forces can stretch its shape, whenever enough time passes for energy to dissipate, synchronization becomes the most stable arrangement. Gravity gently guides the system toward that configuration, again and again, across different planets, across different moons, across billions of years. Seen this way, tidal locking is not unusual at all. It is expected, a gravitational resting point, a common destination for moons throughout the solar system. The same quiet equilibrium appearing wherever the conditions allow it. What once felt mysterious becomes something elegant, a pattern emerging naturally from the laws of physics. This realization changes how we see the moon. The constant face in our sky is not merely a curiosity, it is evidence of a universal process, a visible trace of gravity organizing motion over immense timescales. Every synchronized moon carries the same story, a story of spinning worlds slowly settling into alignment, a story of energy dissipating until equilibrium is reached, a story written not in days or years, but in millions and billions of years. And once we recognize that pattern, the solar system begins to feel different, less random, more connected. Each planet and moon interacting through invisible gravitational threads, each system slowly evolving towards stable configurations. Tidal locking is one of the clearest expressions of that quiet order. It shows us how the universe prefers balance, not instantly, not violently, but patiently, through countless tiny adjustments spread across deep time. The still face of the moon is therefore not a rare phenomenon. It is a glimpse of a broader cosmic tendency, a reminder that gravity does more than hold worlds in orbit. It also shapes how those worlds move, how they spin, how they gradually settle into harmony with one another. And when we look up at the moon tonight, we are not simply seeing a familiar celestial neighbor. We are witnessing the outcome of billions of years of gravitational evolution. A calm, stable arrangement that emerged slowly from the restless motions of the early solar system. One orbit, one rotation, perfect synchronization. A quiet equilibrium written into the fabric of planetary systems. From this perspective, the moon's unchanging face becomes something more than a visual curiosity. It becomes a symbol. A reminder that even in the vast complexity of the cosmos, simple physical laws can produce patterns of remarkable elegance. Patterns that repeat across worlds. Patterns that reveal how the universe gradually organizes itself. And all of it, every synchronized moon, every stable orbit, unfolding silently above us, night after night, just as it has for billions of years. Now, when you look up at the moon, it may feel slightly different. The familiar face in the sky is still there, the same pale craters, the same quiet plains of ancient lava. Nothing about its appearance has changed, and yet our understanding of it has. Because the moon is no longer just a nearby companion in Earth's night sky. It is part of something larger, a pattern written quietly across the solar system, worlds orbiting worlds, gravity stretching them gently, rotation slowing, little by little, across immense spans of time, until motion settles into balance. The same alignment appearing again and again, around Jupiter, around Saturn, around our own Earth. Different moons, different histories, yet guided toward the same quiet equilibrium. One orbit, one rotation, a shared gravitational rhythm. The still face of the moon is therefore not an isolated mystery. It is a visible reminder of how the universe organizes motion. Not through sudden events, but through patience. Through countless tiny interactions unfolding over billions of years. Gravity stretching, friction dissipating energy, worlds slowly settling into harmony with the bodies they orbit. And perhaps that is one of the most beautiful ideas in astronomy. The universe does not always rush. Sometimes it works slowly, quietly, almost invisibly. And yet, those slow processes can shape entire worlds. They can determine how moons spin, how planets rotate, how gravitational systems find their balance. Tonight, if the sky above you is clear, you might take a moment to look up. Find the moon. Notice the familiar patterns of light and shadow. And remember that the face you see is the result of billions of years of cosmic evolution. A calm arrangement created by gravity itself. One small piece of a much larger story unfolding across the solar system. If you're watching this video while looking at the night sky, feel free to share something in the comments. Where in the world are you watching from? Is the moon visible tonight where you are? It's always fascinating to see how many different places on Earth are connected by the same sky. And if you enjoy exploring these quiet cosmic stories about moons, planets, and the hidden patterns shaping the universe, you're always welcome to stay for the next journey. Because above us, the universe is full of these gentle mysteries. Stories written in gravity, stories unfolding slowly across deep time. Stories waiting to be discovered each time we look